kind of where I left off just a little bit. So we got introduced to these exponential functions Tuesday's class. And, you know, here's one. Watch this. 5e to the x. The truth is, I want to add something to this, but I'm just going to wait a second. So we learned about this a little bit. We learned about this Monday. This is an exponential function. Actually, with a base e, it's the exponential function. And what is that number e? It is just a number. It's 2.718 ... It's a kind of a number from nature, a lot like the number pi. It's on your calculator. There's probably on your calculator an e to the x button. And so if you wanted to know what e was, you would have to try to do e to the first. And your calculator would tell you what I just told you. But we're going to need our E button on our calculator. We're going to have to do some calculations. But right now, I'm not calculating anything, and I really don't want to plot a lot of points. What I want is a quick graph of this, and I taught you how to do that the other day. Real quick, you plug in a 0 to get the y-intercept. You plug in a 0 to get the y-intercept, which is really easy because anything raised to the 0 power is a 1. But then a 1 times 5 is 5. So we kind of started to learn that it looks like this number might be the y-intercept a lot of the time. Anyway, it's a 5. And then I had one other great idea the other day when I introduced this, is it's either exponential growth or it's exponential decay. Which one is this? Growth. This is growth. You know that because it has that positive exponent, x. There's not a negative sign on that. That usually flips it to decay. But the other little thing you got to worry about is the base. The base is bigger than 1. The base is e, and e is a number, 2.7. So if it's bigger than 1 and a positive exponent, that's growth. And so here's that good old exponential growth. You ready? There it is. I mean, it's this picture. Sorry, I missed the 5. Should have missed the 5. It approaches an asymptote here, like this. It never crosses or touches or goes below the x-axis here. And this is classic exponential function. And we looked at several of them the other day. And I just wanted to remind you of this. Actually, what I wanted to do was add a little something to this. So I just reminded you of this. And then here's something new that I didn't do Tuesday. Watch this. Let me do this. So now, what if I put a -8 here? So if I put a -8 on that, what does that -8 do? We know this from chapter 4 or 3 or something.
Shifts it down 8.
Shifts the whole thing down 8. The whole graph gets shifted down 8 units. So, hang on. It's a new graph then. Hang on, I'm going to do a new graph. The whole thing gets shifted down 8. And to me, there's two main features of this graph that get shifted down 8. You know, I said that this was an asymptote here. And the name of this asymptote, it's just, you know, it's not really part of the graph. There's the graph. But the graph approaches this asymptote, and it's y equals 0. It's the x-axis. It's y equals 0. Well, anyway, I think that gets shifted down 8. So where's my new asymptote?
Negative.
At -8. At -8, there's a new asymptote. And I think that y-intercept gets shifted down 8. So where's this new y-intercept? Down 8. -3. Right, cool. And then it's just this shape. By the way, back to the y-intercept, there's two ways to think. You know, you could get this graph and then shift it down 8. The truth is you can get the y-intercept, again, plug in a 0 and you always get the y-intercept. You get e to the 0 is 1, times 5 is 5, -8 is -3. So you can calculate the y-intercept of its own accord, or you can calculate this y-intercept and then shift it down 8. It's really the same thing, I guess. Anyway, so here it is. It's this graph shifted down 8. This is a beautiful picture of this graph. But anyway, Tuesday I graphed all kinds of things, but I didn't shift any of them, so I just wanted to shift one. But after shifting one, I got some good questions for you here now. Listen, this is a typical Smith kind of question, and then I might ask these questions. What's the domain? What's the range? What's the x-intercept? What's the y-intercept? Oh, where's that asymptote? Where is that asymptote? That horizontal asymptote. What is that? So, I didn't ask you those questions Tuesday, but I might like to ask you those questions now. So, what did we do? We took a look at this graph. We shifted it down 8. We got a great picture of it here. So let's try to answer these questions. I'll get rid of this picture. This is not the picture. It was the picture before you shifted it down 8. So there's the equation. There's the picture. We shifted it down. And now let's try to answer these questions. Do you know the domain of this function?
All room.
Yeah, what are you allowed to plug in for x? And you can think about the equation, what do you plug in for x? But once you have a graph, maybe you realize that it spreads out over all x's. He said it's all real numbers. So he's right. The domain is all real numbers. But maybe you can tell and see that the range is not. What is the range? The range is the y values, and it's totally dictated by that horizontal asymptote. This will not go below -8, and it won't touch -8 either. So what's the range? Greater than? Greater than 8. Y is greater than -8. Yeah. You can say it like that. Hey, there is an x-intercept, isn't there? Oops. Sorry about that. You know, a few minutes ago I had this, before you shifted it down. In fact, all day Tuesday, we had exponential functions like this. They either were growth or they were decay, but I didn't shift any of them Tuesday. And so all day Tuesday, what were the x-intercepts? I didn't even ask you. I didn't even think about it, because what are the x-intercepts? There aren't any. It doesn't touch the x-axis. Now, as soon as you shift it down, now it does. So now there's an x-intercept, and I can see it. And to find it, I got to teach you some stuff. Let's just skip that for 2 seconds. What about the y-intercept? You see it, we've already labeled it. You could go back and plug in a 0, but we've already labeled it. And what about the horizontal asymptote? It has a name. It's this line. It's this dashed line, and its name is -8. Really, its name is y equals -8, because it's a line, and that's how you name a line. Y equals -8. Cool, we did great. But let's check out this x-intercept. This idea is gonna carry me into the future here a little bit. I mean, in order to find an x-intercept, what do you always do? You know what you do. You've been doing it all semester. If you want to find an x-intercept, you plug in a 0 for y. If you plug in a 0 for y, now you have to solve for x, right? All right, I bet you could get started, but I don't think you could finish. Maybe you could. How would you start? Add 8. Thank you, I would add 8. What would you do next? Divide by 5, I would too. Divide by 5, divide by 5. You could call that 8/5. It also happens to be 1.6, I think, if you actually do it. All right, I'm happy with that. But now, I have to I have to un-e it. I mean, this x is up in the exponent, and I got to get it out. This x is being base e'd, and I have to unbase e it. I mean, this is new algebra territory for us. What I need is the inverse function of the exponential function. I need to unexponentiate that. Anyway, in order to do that, mathematicians have invented logarithms. So you could act like logarithms are some mysterious thing. Maybe that's how I'm acting. But I'm telling you, what I'm doing is, here's what I'm doing right now, is I'm showing you the purpose of logarithms without really even teaching you what the heck they are. The purpose of logarithms is to help you solve exponential equations, because logarithms are the inverse of an exponential function. And so I have to unbase E this. And I'm going to just tell you what this is without really explaining the guts behind it. I do an algebraic step called take the log of both sides. Because we're dealing with the special E base, then we have a special logarithm. It's the natural logarithm. Again, E sort of came out of nature, so his inverse is not just any logarithm, but the natural logarithm. And the notation for the natural logarithm is an ln. So I do the ln of 1.6, and I do the ln of e to the x. Again, I haven't really explained this too greatly, except I'm totally telling you that the ln function is the inverse of the e function. And so when you ln and e, it's almost like, if something was multiplied by 3 and you divided by 3. Or if something was squared and you square rooted it. Or if something was cubed and you cubed it. I mean, it's the inverse of the e base. And so on this side of the equation, the ln and the e cancel each other out because they're inverses of each other, and we get the answer x. And the answer x is this, the ln of 1.6. Listen, ln is a function. It's a button on your calculator, and you could probably find your ln button and punch in the ln of 1.6. Maybe you hit 1.6 and then you hit the button, or maybe you hit the button and then you hit 1.6, depends on your calculator. Can you tell me an answer? And this would be an approximate answer. What'd you say?
0.47.
0.47. You know what? I think sometimes we get a habit of 3 decimals here in chapter 5 for some reason. I'm not sure if the math lab, but so give me one more decimal.
0.
470, huh? Okay. You guys agree? Mm-hmm. All right. Cool. I guess that's my, what's that? That's my X Intercept. Hey, one of these is an exact answer. The other one has been approximated with a decimal. I call that exact. And then this is my decimal approximation. It's been rounded off, right? Cool. Well, so, I like to see your work. I like to see everything. If you're working on the homework in my math lab, I'm not sure what they want. And if I see your work, I can see both. I'm happy. What should you go over here and list? I don't care. If I see both of those, I don't care. But maybe again, I'm kind of after the exact answer. So I'm saying that's my X Intercept. But in order to put it on a graph or think about it, I need a decimal. It's approximately 0.47. It's approximately 0.47. Cool. So I sort of just introduced you to logarithms. I didn't really tell you what they were, except that they're the inverse of an exponential function. And, again, in Tuesday's class, we did a lot of different exponential functions with a lot of different bases. Base 2, base 5, base 10, we did a lot of stuff. And then we ended up at base E. Well, so there's a lot of different logarithms with different bases. There's log base 10, there's log base 2, there's log base 7. Anyway, for this problem, since it was base E, I used something called log base E. But log base E is very special. It has a name called the natural logarithm. So there's other logarithms with different bases. This is special. This goes with the E. It's the cousin of the E function. It's the inverse of the E function. One more little comment. Students, what I'm doing is I'm taking the log of both sides, and some students look at that and say, oh, he multiplied by an ln. That's really kind of bad. I don't like that. You're not multiplying you're not multiplying by the letters L and N. It's not multiplication. It's a function called the natural logarithm, and we're doing that function to both sides. And it's not multiplying. It's like this thing. See this thing? When you have this and you try to solve, you take the square root of both sides, don't you? And you wouldn't tell somebody, oh, you're multiplying by one of these. You wouldn't tell somebody that, would you? No, good. So that's the same with this ln. I'm not multiplying by some L and N. I'm doing the ln function to both sides. I'm taking the log of both sides. And you don't really know what taking the log means. I haven't explained that yet. I will. But I like to get to the point. So the point of log, we can go back and have a big, lofty discussion about logarithms, and it's cool, we need to maybe, to understand what they are. But the point of logarithms, I'm telling you, the point is to help you solve exponential equations, to help you unexponentiate something. In fact, let's just do one more example like this. Watch, so at the end of class, Tuesday, the other thing I did was I got into just a little bit of a finance problem where we used this formula, S equals P e to the RT. Now, this is for putting some money in a bank. The bank pays me an interest rate, compounded continuously, and if they pay me interest and I leave my money in there, my money grows. So the P is the original amount of money you put in the bank, and then it grows, and S is the final amount of money you get after so many years. By the way, that works. That also works when you borrow money from the bank or on a credit card. If I borrowed a bunch of money on a credit card, they charge me interest, and the amount of money I owe them grows. You know, so it can work kind of forwards or backwards, or it's the same thing, really. I'm either saving money and the amount I'm saving grows, or I'm borrowing money and the amount I owe grows. You know, usually when you borrow money, you make payments. But there would be no payments here. So let's pretend this. Let's pretend this. I maxed out my credit card, you know. I maxed out my credit card, my Visa card. $2,000, it was a $2,000 limit. I maxed it out. They charge me some interest. They charge a lot of interest, don't they? Sometimes those guys charge a lot of interest. I'm going to say they charge me 16.8% interest rate. And in order to use this formula, I think you kind of need the phrase compounded continuously. My math lab or my book might disagree a little bit, but I think I need that phrase that tells me I'm using this formula here. So there's an interest rate, it's compounded continuously, I've got that. And then here's the question, this all happened, this was 12 years ago. So I maxed out my Visa card. I never made any payments. I changed my address. I tried to go lay low. This was all 12 years ago. So what's the question? How much do I owe? Right. How much do I owe Visa? How much do I owe? It's not going to be good, I don't think. It's not going to be good. It's really easy to use this formula in a way. Here we go, here we go. I guess S is what I'm looking for, the sort of the future amount of this. But I started with a balance of $2,000. I have this base E, it's just a number E, you guys, raised to the interest rate is 16.8%. When you use this interest rate in a formula, you turn it into a decimal. You don't put a percent. So you take the percent, you make it a decimal, which would be 0.168 times the 12 years, I guess, right? Is that what's going on? The interest rate times the number of years you left it in there. All right. You know, depends on your calculator. Some of you can just type all this in straight like it looks on the board. Some of you might do little baby steps, like multiply that, then E it. You got to find your E button. and then multiply by the 2,000 last. Anybody want? It's probably I don't know. It's probably a lot, like I don't know, $30,000 or $40,000. Maybe it's not that much. $20,000 or $30,000. I'm guessing. $100,000. It's not too much. How much is it?
15,000.
15,000? That's all?
That's 17. $15,017.
Okay, that's not bad. I could probably negotiate with them somehow. $15,017 and some cents, please.
Oh,
It would be $16.46.
Oh, $16.46. You guys agree?
mm-hmm.
Okay, good. I mean, we want to, yeah, let's do it as accurate as possible. And when we're talking money, we'll go to 2 decimals for money, for pennies. Get the pennies accurate. They're not going to forgive, Visa's not going to forgive those pennies. Cool, that wasn't as bad as I thought. Luckily they gave me a cap of $2,000, otherwise I would have went crazy back in the day. All right, that was easy. Okay, watch this. Here's something new. You ready? This is new. This is what Visa says. Here's an so part A is, how much do I owe? Thank you very much. Okay, part B. This is a new cool question. You ready? Part B. Visa wants to know, when will he owe $1 million? Sorry. It was supposed to be an impression of somebody.
Good effort.
Good effort. Thank you. So this is good. See, anyway, now that I know just a teeny bit about logarithms, I can ask you this question. Because now, what are you doing? So when, I think, means he's asking for the time. We're asking for the time when it reaches $1 million. So back to this equation, I think this would be $1 million over here. Make sure you get the zeros right. That's my $1 million. The original principal was 2,000. The base is E. The interest rate is the 0.168. But what I don't know is the time t. Right, how many years will it take to be $1 million, right? So now I'm solving for t. And in order to solve an exponential equation, we're going to have to get rid of the e. We're going to have to use our ln again. That's what we learned a few minutes ago. We can take the ln of both sides. But wait, you don't do the logarithm yet. When you want to do the logarithm is when you can get it next to the base, because the logarithm kills the base. Right now that 2,000 is in the way. You guys are smart. You would have thought that yourself probably anyway. Step 1, divide by 2,000, don't you think? Divide by 2,000. That kind of exposes the base e. And then I can solve this, I think. What is this? 500? Thank you, 500. All right. So now the e is exposed, and if I want to get rid of the e, I do the inverse of e, which is a logarithm called ln. So I do the ln of both sides of this equation, just like algebra has always taught me. Whatever you do to one side, you do it to the other side. So I'm doing the ln of both sides of this equation. On this side, I got the ln of 500, which is some decimal. I'll punch that in my calculator later. Right now, what's going on this other side? I have the ln of this e. What happens here? You know what happens here, maybe. They cancel because they're inverses. That's the idea. And so I'm left with 0.168 times t. All right, I got to find t then. Divide by 0.168. Okay. So in a way, this is the answer. How many years did it take? Well, there's the answer, Mr. Smith. But I'd prefer you now pick up your calculator and actually tell me the number here. This might be 80, 90 years. I don't know. Pretty long time. I mean, what was
30,
this one?
37.
37 years?
Or 36.99171.
That's all?
That's how I did it.
See, again, that's the...
3699.
That's that exponential function. I mean, it grows quicker than you think, kind of. I mean, it took 12 years, right? 12 years, and I owed him $15,000. But another 25 years, you said a total of 37 years, huh? And then now I owe him $1 million. Yeah. That's right. Make your payments. You can't disappear. What did I say? I said something once about rounding to 3 decimals. When it comes to the years, the number of years, sometimes the tenths place is good. But I think he said 36.99. Is that what he said?
Yeah.
Well, then the tenths place is 37.0, I think. So 37 or 37.0. Cool. All right. Well, cool. So a couple of problems from 5.1 with a couple of added thoughts using logarithms here. What I want to do now is actually introduce you to logarithms and explain something to you. But I'm going to take a quick 2-minute break, and then I'm going to come back